Where do we get magnetic fields? These are produced by currents, and there is what looks like a relatively simple formula that will let you find the magnetic field at any point caused by a current anywhere else. The tricky part of this is it's only simple looking. This is called the Biot-Savart law, and it looks like this. We have B is the integral of this mu naught over 4 pi, then I dl cross r hat over r squared, and we can see with this picture from the book what all these pieces are. I and dl are of course in the same direction. This is the current in this tiny little element of wire length, and then r hat is the direction towards this point with the x, which is where we want to know the B field. Now, using the right hand rule, you can put the thumb of your right hand in the direction of this current, and your fingers would wrap around the wire above here, around the side, underneath it, back up. So here your fingers would be going into this, down. Now the problem with this, first we can look at the constant if we want. This constant mu naught, this is the permeability of free space. This should remind you of epsilon naught, the permittivity of free space that we saw with Coulomb's law and Gauss's law. We've discovered later when we were looking at capacitors that everything has its own permittivity, and there's a very large range of these values. Everything also has its own permeability, but it turns out that for almost everything, the permeability is the same as it is for the vacuum. The big exceptions are iron, nickel, cobalt, other things that you can make magnets out of. One consequence of this fact, all these things having the same value of mu, you imagine you're holding a magnet a few centimeters above an iron plate, and you can feel it pulling towards the plate. You can put your hand in that gap, or paper, or aluminum, or practically anything, and you won't feel a change in the force. Of course, if you put a piece of iron in there, you'll feel that change. Anyway, the value of mu naught is 4 pi times 10 to the negative 7 Tesla meters per amp. You may remember that we've got a formula that lets us figure out the electric field at a point due to any random collection of charges. Right here, this is Coulomb's law, essentially. We didn't actually want to do this because unless the charge distribution is very, very symmetric, we don't want to do this analytically. We can do it numerically if we have to, but it's sort of the last resort, or it's what we would do if we were going to have a computer do it. Now, as bad as this would be to integrate, the Biot-Savart law is worse, because if you look at this, the only directional part is from the point of interest to the point where the charge is. We just have that one vector piece of this. If we go back up here, we have the vector current, the vector direction from each little piece of current to the point of interest, and we have to find the cross product of those two things, and that's going to be a horrible mess unless, again, something is very, very symmetric. So we're going to do a couple of examples, but remember we got out of having to do this Coulomb's law by using Gauss's law, and it's going to turn out that there's a similar law that will help us avoid using the Biot-Savart in most cases. First, we want to find the field near an infinitely long straight wire. And again, we don't do this because we want to be able to do infinite wires. We do it because if our distance to the wire, shown here as capital R, is very small compared to the length of the wire, then the wire is essentially going to look infinite. So we look at the little tiny current element dx here, carrying a current I. Again, you can put your right thumb, point it this way to the right. Your fingers will curl around above this, out of the page above this, and into the page below it. So the field at the point P should be out of the page. Anyway, how big should it be? Well, we'd have to find the cross product here of the R and the DL. And when we do this, we can write it like this. Cross product is I sine theta dx, where that takes care of the R hat and the DL, the direction. This is all over R squared. Now, we could also write this sine of theta, because sine is opposite over hypotenuse, as capital R over x squared plus capital R squared, the square root of that. That's little r. So capital R over little r is sine theta. So we put that in and we integrate from negative infinity to infinity. What we could also do, though, is just multiply by 2 and integrate from 0 to positive infinity, since it's an even integral. So we get b is mu naught I over 2 pi times this integral from 0 to infinity, capital R over x squared plus r squared to the 3 halves. We integrate with respect to x. This is not the easiest integral in the world, but it's also not the hardest. The answer that you get is mu naught I over 2 pi r. What we notice that's interesting here is the magnetic field due to a long straight current has the same distance dependence, 1 over r, that we got for the electric field due to a long straight charged wire. Now that we know the B field, we can look at an interesting problem. What's the force if we have two parallel current carrying wires? Let's say they're carrying currents I1 and I2 and they both are going to the right and they're a distance d apart. What's the force on one of these due to the other one? We need to know what their magnetic fields look like. So, for example, in the red, you point your thumb to the right, and the fingers of your right hand will be coming out of the page above this wire, and they'll be going into the page below it. So all these X's are, of course, into the page. The green is going in the same direction, so we get the same thing. Above it, out of the page for the magnetic field, and below it, into the page. Now, if we want to know the forces, let's look first at the force on this red current I1 due to the magnetic field from I2, which is green. Everywhere around it, the green is out of the page, right? So we can figure out from the ILB sine theta rule, we know the angle between the B field, which is in or out of the page, and the current, which is left or right across the page, is 90 degrees, so sine of theta is 1, and this disappears. Now, if these wires are infinitely long, the L is not really going to be helpful to us. We'll get an infinite force. So what we usually do here is find the force per length. So now what we're looking for is I1 times B2. Now, we just figured out how to find B2, the current due to current, the magnetic field due to current I2. And B2 is going to be mu naught I2 over 2 pi d. So we multiply that by I1, we get mu naught I1 I2 over 2 pi d. What's the direction of the force? Well, we see here we can take the fingers of your right hand, point them in the direction of I, which is to the right, and then they have to curl into the direction of the B field, which is out of the page. For your fingers to point right and then curl out of the page, your thumb will be pointing down. That means it'll point towards the other wire. What about the force of 1 on 2? We apply all the same logic. We end up with I2 times this B1. Notice it looks exactly the same, mu naught I1 I2 over 2 pi d. Now what about the direction? So here, B1 is into the page, the red X's that surround this wire. We would point your fingers to the right, then curl them into the page. That's going to leave your thumb pointing up. This is actually not really a surprise. These two things, we have to have this relation between them because of Newton's third law. We have to have that the force of 2 on 1 is equal and opposite to the force of 1 on 2. The odd thing is, now we have two things that are alike that attract. Ordinarily, like charges repel, but here, like currents attract. What if we change one of the currents? So we change the lower one to move left. Of course, none of the red things change. But now the green things, we move the current to the left. That means our magnetic field is into the page on top and out of the page on the bottom. So what's our direction at this point? Well, the direction here at I1, our force would be, take your fingers and point them to the right, curl them into the page. Now your thumb is pointing up and away from the other current. Down here, take your fingers, point them to the left, curl them into the page for the B1 field, and your thumb is pointing down. So opposite currents repel. Now, it's interesting to see how strong this repulsive force is. Let's look at jump starting a car again. Let's say the jumper cables are carrying 400 amps of current. I think this is way more than they would carry, but 400 amps of current down one side and up the other. We'll assume the centers of the two wires are 2 centimeters apart. What's the force of repulsion per meter? Well, mu naught, which is our constant, times 400 one way, 400 the other way, divided by 2 pi d. This gives us 1.6 newtons per meter. Now, if these are 4-gauge jumper cables, which is common, made of copper, their weight would be about 3.7 newtons per meter. So this isn't a huge force. This is less than the weight of the wire. So if you cut the wire, if you split the jumper cable in two, it's not like they would be pushed apart enough to levitate one of them or anything interesting like that. And again, this is a ridiculously large current that we don't normally encounter, and it's very, very close to another current. So this is really kind of the top end force. In general, this force is negligible. Now, we can look at another relatively simple geometry to find the magnetic field. Here we have a current loop, and we want to find the magnetic field above it. Remember when we had a charged ring like this, we had cancellation from opposite sides of the ring, and the only part that was important was the part that was perpendicular to the ring. So we're going to have something similar there. We'll say our point of interest is on the y-axis, and that's the loop's axis also. The loop's radius is capital R. The point we care about is a distance y above the center. They go over this in your book. The field dB, this little piece here, due to the current element dl, is mu naught over 4 pi I dl sine theta over r squared. Here we get that reduces to mu naught I dl over 4 pi y squared plus big R squared, because that's our little r right there. Now the components parallel to the plane of the loop cancel, so we have to have a cosine theta in there. And what we get out of this, we can again find cosine theta as r divided by square root of y squared plus r squared. We get this mu naught times mu over 2 pi y squared plus r squared to the 3/2. This is in the y direction, or the j hat direction. Mu that we've defined here is I times A. That's a magnetic dipole moment, remember. Now, if we go to the center of the loop, y equals 0. So what do we get for the magnetic field there at that point? We get mu naught I over 2r. Now, don't confuse this with what we got for an infinitely long wire. That was mu naught I over 2 pi r, and that was a variable r rather than the size of a loop or anything. So remember, we also don't have that pi here for the loop. So we can find B fields like this, but we're not going to enjoy it. What's the alternative? We have something like Gauss's law is for E fields, and it's called Ampere's law. It looks like this. We've got integral over a closed loop of B dot dl is mu naught I enclosed, which we can also write that as mu naught integral current density J dA. Remember, Gauss's law looked like this. Integral over a closed surface, E dot dA is Q enclosed over epsilon naught, or 1 over epsilon naught integral of rho dV. So what we're saying is the integral of this B dot dl around a closed loop is proportional to the current that goes through the loop. We should notice there are multiple similarities to Gauss's law when we go through this. First, let's find something we know. Let's try and find the B field at distance r from our long infinite straight wire. We already know this answer, and as with Gauss's law, we're only going to use this in cases where we have high symmetry. So if someone spells out their name in fancy script with a wire, we're not going to be able to find the magnetic field due to a current through that wire easily. Now, a circle that has the wire's axis at its center is the best choice for our Amperian loop. This is our imaginary thing like our Gaussian surface. This could be a horrible integral on the left, this B dot dl. This could really be miserable. But turns out this is going to be very simple. As we move around this loop, there's no way for the magnitude of B to change, because just like with Gauss's law, I don't have a top or a left or a right. I don't have anything that allows me to pick out part of the loop and say, oh, it's stronger here and weaker there. So the magnitude of B has to be constant going around here. Now, if I take the thumb of my right hand and point this way, my fingers curl the way this red arrow is already going. So B is parallel to DL. I don't have to worry about the dot product. On the left, I get a much simpler integral like we always did with Gauss's law. What's the distance around this path? Well, all I have to do is integrate r d theta from 0 to 2 pi. That's what we get. We get 2 pi r. So it's the circumference of the loop times b. That's the easy part. On the right, all I get is mu naught times I, because the current enclosed is I. So I can solve this for b as mu naught I over 2 pi r. So it's reassuring that it matches what we had before. What if we have an actual physical wire rather than this imaginary 1D filament? For right now, let's assume the current density is uniform. So in other words, if the wire is made up of many smaller strands of wire, each strand carries the same current, whether it's near the center of the wire or near the surface. That's what makes J a constant. For a physical wire, we can look at the B field inside and outside the wire. We'll say the wire's radius is capital R, and we'll look at the field inside, where little r, our Amperian loop, is smaller than big R. Now, as before, the integral on the left gets much, much easier. We still have no way for B to change in magnitude as we go around. It's still going to be in the same direction. So we're going to get the same thing over and over and over again, B times 2 pi R. On the right, we have to see how much of the wire is inside this dotted line. The integral is mu naught integral of J dA. Now, what does our area element look like here? We've actually done this before with Gauss's law. We imagine a tiny square on the face of this cylinder, or here, in our Amperian loop. We look at that and we say, okay, if one side is in the r direction, dr, that would be our length. The other way, that's the theta direction, but d theta isn't a length. We have to have the r in there to make it a length. So the area of this little tiny square is r d theta times dr. This is again a double integral, which at first is scary, but we remember this is going to be an easy one. The theta integral is just 0 to 2 pi, and there's nothing to integrate here. The r integral, the only thing we're changing here, we're changing this to r prime and dr prime because, again, the math people don't like it if your variable of integration is the same as one of your limits of integration. It's not professional. So when we do this integral, we just get 2 pi out of this one. That's trivial. Then we end up with the integral 0 to r of r prime dr prime. That's an easy integral. That's going to give us r squared over 2. So here's what we get on the right. And that simplifies to mu naught J pi r squared. So I can divide by what I got on the left. I get B is mu naught JR over 2. Now, since J is constant, that's just I over A or I over pi big R squared. So I could also write this B is mu naught IR over 2 pi big R squared. What about outside the wire? Now, the left side doesn't change. We still have the magnitude of B being constant around the loop and in the same direction we're walking. We get the same thing on the left every time we've done this so far. B is 2 pi R, B times 2 pi R. On the right, it's almost the same. This time, though, instead of integrating out to little r, the Amperian loop, we stop here at the surface because that's where the current density stops. We don't have current all the way out here. So we integrate on the right, mu naught times J, integral 0 to 2 pi d theta, 0 to big R of r dr. We get mu naught J pi r squared. Now, just like with Gauss's law, on the left we always integrate out to the imaginary thing, here the Amperian loop. On the right we integrate to the smaller of the imaginary or the physical thing. If you want, you can say you're always going to integrate out to the Amperian loop on both sides, but then the integral on the right, you have to take the change in J into account. So your integral from 0 to little r breaks into 0 to big R, where you have a current density, and then big R to little r, where you don't. So you don't end up doing this anyway. However you want to do it, that's fine. We put the left and right together. On the left, B times 2 pi little r. On the right, mu naught J pi big R squared. or B is mu naught J big R squared over 2R. Now, as before, as long as we're in this course, we're going to get the same if we use either formula if we're at the surface where little r equals big R. If you notice, mu naught I R over 2 pi R squared. If R equals big R, we just, one of these cancels and we get 1 on the bottom. And the same thing happens here when we move down here. So, like we did with Gauss's law, let's say we look at, if we rewrite J as I over pi big R squared and plug that in here. So we got mu naught R squared over 2 little r times I over pi R squared. R squareds cancel. We get mu naught I over 2 pi R. Just like with Gauss's law, we're outside of this wire. We get the same thing that we would get from the infinitesimal 1D wire. What about if the current density is non-uniform? You may have predicted that the current density can only depend on R and not theta. Again, the reason is symmetry. So this is as crazy as it'll ever be for us, some polynomial dependence of R. If we say J is C R to the 4th, that means the current would rather be on the surface. It's more dense there than the center. What do we get on the left? You can guess. We get the same thing we got before. On the right, and we're doing this inside. So on the right, same theta integral. Our R integral, again, we have to use R prime. We have the R prime dr prime, but we also have the C R prime to the 4th. That represents our J. We do this integral, not too bad. Mu naught 2 pi C R to the 6th over 6. That's equal to the integral we got on the left. We solve for it and get B is mu naught C R to the 5th over 6. Any polynomial would be just as easy. It would just look different. We do it outside and it's almost the same as we got for the constant J. Everything's the same on the left. On the right, we integrate to big R instead of little r, and we get mu naught 2 pi C big R to the 6th over 6. We put that together with the left, and we get this solution. Again, if little r equals big R, they match. And we see one more thing. What's the total current in the wire? That's integral of J dot dA. So I could say 2 pi C R to the 6th over 6 equals I. That means I could replace C with 3I over pi R to the 6th. What happens to our formula if I do that? We get mu naught I over 2 pi R again. So if we're outside the wire, as long as our current distribution doesn't depend on theta, it's going to look just like the current I at the center of the wire.